We are solving question number 41 of GATE 2019 Chemical Engineering paper. And the question is related to process fluid mechanics subject. A centrifugal pump is used to pump water density 1000 kg per meter cube from an inlet pressure of 10 raised to 5 Pascal to an exit pressure of 2 into 10 raised to 5 Pascal. The exit is at an elevation of 10 meter above the pump. The average velocity of the fluid is 10 meter per second. The cross-sectional area of the pipes at the pump inlet and outlet is 10 raised to minus 3 meter square, and the acceleration due to gravity is g 10 is equal to 10 meter per second square. Neglecting the losses in the system, the power in watts delivered by the pump is dash rounded off to nearest integer. So first of all, in this question, we have been given a centrifugal pump. And it is used to pump water with density of 1000 kg per meter cube from an inlet pressure of 10 raised to 5 Pascal to an exit pressure of 2 into 10 raised to 5 Pascal, and the exit is at elevation of 10 meter above the pump. So if this is our suction of the pump over here, let's just call it as 1. At 1, the pressure is 10 raised to 5 Pascal, and the exit is 10 meter above the suction. So if this is the exit, then this will be 10 meter. Let's just call it a second point. And at second point, the pressure is 2 into 10 raised to 5 Pascal. Now we have been given that the cross-sectional area of the pipe at inlet and outlet is 10 raised to minus 3 meter square. So area at 1 is equal to area at 2. Both the areas are same as 10 raised to minus 3 meter square. Gravitational constant is given as 10 meter per second square. Neglecting the losses in the system. So it has been given that the frictional losses should be neglected. So we'll just consider it as 0. Then we have been asked the power delivered by the pump is dash. Power we have to find. And power we usually write it as mass flow times of work done by the pump. So over here we can write the mechanical energy balance over this system. That is, we can write the Bernoulli's equation for this system, and then we can find the desired terms. So if we consider these 2 points 2 and 1, for that we can write P2 minus P1 upon rho plus G. So over here height is, let's call it, this is height is H2, and over here height is H1. If this is our reference, we can call this height 1 as 0, and this height 2 will be 10 meters. So let's just write it H2 minus H1 plus 1 upon 2 alpha V2 square minus V1 square plus summation of F plus work done is equal to 0. Now over here, we have been straight away given that we have to neglect the losses, so this term will be 0. Now since the area is same from the continuity equation, rho 1 A1 V1 is equal to rho 2 A2 V2, we can say that V1 will be equal to V2. That implies this term will also be equal to 0. Now we have been left with these other 3 terms, using which we can calculate the work required to transport the water from 1 to 2. So over here we can write that P2 is 2 into 10 raised to 5 and P1 is 10 raised to 5 Pascal. So P2 minus P1 will be 10 raised to 5 Pascal upon density we have been given as 1000 kg per meter cube. Then gravity constant is 10 meter per second square, and height H2 minus H1 is 10 meter. So this will be equal to work required. This we can write it as 100 plus 100. The unit will become, over here it is meter, so it will become meter square per second square. is equal to minus of W. So this is equal to 200 meters 200 meters square per second square. So the work required we found out as 200, and in the question we have been asked to find the power. So power is defined as mass flow rate times of work done. So mass flow rate we can calculate using this rho AV into W. So density is 1000. Area we have been given as 10 raised to minus 3 meters square. 10 raised to minus 3 meters square into, then velocity is 10 meter per second, and then we have been asked then we have found out this work, so that is equal to 200. So this we can write it as 2000. So if we write the units over here, it was meter square per second square, then this velocity is in meter per second, 10 raised to minus 3 is again in meter square, and this is kg per meter cube. So basically we can write this as kg upon meter cube into meter square, meter cube upon second into meter square upon second. So this will get cancelled out, and basically kg meter square upon second cube is, you can call it as watt. So this is basically watt, 2000 watt. So the power delivered by the pump is 2000 watt. So we can write the final answer as 2000 watt.